I want to back up for a minute and just make sure that we are absolutely comfortable with something I was saying, okay? So we were doing these we did a proof by contradiction last time, right? And remember, when we do these proofs, the goal, hang on a second, this pen is not on right now. Here we go. So the goal is to prove P implies Q, right? So that's the goal. You want to prove that Q follows from P every single time, yeah? Now, most of the techniques that we use, we start by sort of assuming the truth of P and working from there, or assuming the truth of not Q and working towards not P. That second method I just said, that's called proof by contraposition, yes? So we either assume the truth of P and work towards Q. And by the way, why is that valid? Like if I'm trying to prove P implies Q, why is it valid for me to go ahead and assume that P is true? Isn't that kind of like getting the cart ahead of the horse a little bit? Yes, yes. That's exactly right. Like if P were false, like who cares, right? If P were false, the conditional would automatically be true. False implies whatever is going to be true automatically. Therefore, it makes sense that we just go ahead and assume that P is true at the beginning. Similarly, when you prove the contraposition, you assume that not Q is true and you kind of work from there. But contradiction is kind of a different animal. You start with something and you kind of use that as your starting point, but you don't like really think of that as necessarily being true. I think this is where people get tripped up. So, and in the end, when you're doing contradiction, what you do is you show that P and not Q, okay, that this thing implies, I don't know, some capital Q, all right? So you kind of show that this is true. So this is kind of the first step. You show that P and not Q implies Q. You show that this statement is true, yes? Okay, and the second thing, you don't really show this, it's just sort of obvious. You show that Q is false. Okay, so if that's the case, right, so look at this conditional right here. Okay, this entire conditional is true. Let me put some parentheses around here just so that it's totally clear what we're saying. That conditional thing implies capital Q is true and Q is false. What does that tell you about? What does that tell you about P and not Q? So you can actually make a conclusion from that. Therefore, what? P and not Q is false. Is equivalent to false. Okay, and so forth, you can say, okay, therefore what? The negation of P and not Q is equivalent to what? Look, if P and not Q was false, the negation of that would be true, right? But let me just kind of point this out as kind of a last thing. The negation of this, of course, is just equivalent to the negation, or what is that? That's going to be not P, right? Not P or what? Q, which, by the way, is logically equivalent, as we know, to what? P implies Q. That's exactly right. So that kind of establishes the validity of contradiction, yes? So really, you're not really assuming, when we assume this, right, that this is where when we assume this, okay, we're not necessarily assuming it is true, okay? Just sort of our starting point, and then we have a chain of logical implications from there, and each of which happens to be valid, and therefore the implication itself is true, yes? So it's a little bit different the way operationally this thing works from other techniques. Yes, sir?
So on the first one, the thing actually isn't true, but we're assuming it's true to prove.
No, I mean, you're using the word assume differently. So you're saying, I'm assuming this, and what you really mean is that you're just starting from this thing, okay? I mean, you could you can assume whatever you want as kind of a starting point to an argument. I can assume that pigs fly, for instance. Yes? And I could try to see what's implied from that. Yeah? I mean, logically, we'll do silly things like that all the time. We'll say, well, let's just, okay, I'm going to assume your position, this, and then you kind of show that it leads to some kind of nonsense. Okay? So, I mean, you can assume whatever you want at the beginning, but you're not necessarily assuming that it's true. In the other proof techniques, though, you really are kind of assuming that it's true because you can. There's no danger in doing that. Does that make sense? Because as somebody already pointed out, starting with P being true, you might say, well, how do I know that P is true? I might be in a situation where it's not. Well, in those cases where it's not true, the implication is automatically true. Does that make sense? Okay, so you might as well assume that it's true. Okay, I just want to be extra careful with that, okay? Just make sure that you all believe that contradiction is a valid proof technique, okay? And one thing I wanted to do, the reason I wanted to do that is I want to show you kind of a pretty cool proof, okay? That uses contradiction, and I want to do that right now. Okay, so let me see here. I'll go to the whiteboard. You guys saw this in your Heart of Mathematics. You guys saw this in your Heart of Mathematics. Oops, what is going on here? I'll unpin that. Heart of Mathematics book, but I think the proof that they give in there is a little awkward, okay? So here's what we want to show, okay? So the claim is that the square root of 2 is irrational. Okay? Square root of 2 is irrational. Now, it might not be clear to you how to kind of frame that as an implication, but it is possible, okay? What you do is you say something like 2 is an, 2, actually, there's a much more general statement you can prove here. Like if you have a prime, so if P is a prime, then the square root of P is actually irrational. So let's actually supersede this by proving another claim. Here's a claim. P prime implies what? So P prime implies what? The square root of P is irrational. Okay, do you see that this has the form, we'll say capital P implies capital Q or something like that, yeah? And do you see that since 2 is prime, then of course, if we could prove this statement right here that P prime implies the square root of P is irrational, since 2 is prime, that would automatically follow as a corollary, or corollary if you're a Roper, right? It automatically follows that the square root of 2 would be irrational, yes? But this is actually a more powerful statement than that. Okay, so here's the proof. Okay, what do we kind of assume? Okay, so let P be prime, and suppose the square root of P were what? Yeah, that's right. Okay. You guys see that this is like assuming, I mean, here I want to parenthetically remark, this is like P, capital P, and what? Not Q. Okay. So I just want to make sure that that's clear, that we are indeed proceeding by contradiction, yes? Okay. What does that mean? If the square root of P were rational, what does that mean? What does that mean? What does it mean for something to be rational? That means it can be written as a ratio of integers, yes? Okay, then there are integers, let's say A and B, such that the square root of P is equal to A over B. And there are some things we know about B, for instance, like B can't be 0, for instance, right? I mean, of course, B couldn't, something that's in the denominator couldn't be 0, okay? Yeah? So far, so good? All right. Do you guys remember what they did? Now, in the heart of mathematics, they like assume stuff about, well, let's put this thing in lowest form, etc. And they sort of proceeded in that way, but that's actually not necessary. Okay? We can actually very easily get a contradiction from here. Okay? And it has to do with uniqueness of factorization. And there's a little theorem called the fundamental theorem of arithmetic, okay, that talks about that there's only one way to factorize an integer into a product of primes. So for instance, if somebody came in here and said, hey, quick, go factor the number 88 into its primes. There's no way that if Monique and I went into separate rooms for a few minutes and then came back that we would have like different factorizations. Does that make sense? We would have to have the same factorization if indeed we proceeded correctly, okay? Okay, so the factorization of 88, by the way, is like, what, 2 cubed times 11 or something like that, yeah? Okay. And that's unique. There isn't some other way to factorize that into primes. Didn't you guys used to do that in elementary school? Like you'd have the number and you would make the little factor tree and you would keep breaking it down, remember that? And then you would like take the little leaves of the factor tree and those numbers would be the prime factorization. I used to love doing that, but hopefully you guys remember that, okay? Okay, so watch this. Then P is equal to what? A squared over B squared. So watch this. P times B squared is equal to A squared. Okay, that's interesting. Okay? Yeah? Okay, so what is the contradiction going to be? So note that, let me just write something. Note that, for example, 88, oops, I meant to write 88 and I wrote 8 minus, okay? 88 is equal to 2 cubed times 11, yes? To the first power. And so 88 squared is equal to, okay, so like, what's gonna happen when I square 88? What happens to the prime factorization of 88? All of those primes get doubled in quantity, yes? So it's gonna be 2, not to the third anymore, but 2 to the 6th times 11 to the 2nd, okay? Which consists of an even number of primes, right? Of course, if all of the primes individually get doubled, then if I add all those together, I'm gonna have an even number of primes total. What's the total number of primes in this case? I mean, I'm not trying to insult your intelligence or anything, but what's the total number of primes? There are 8 primes. Yes? That is guaranteed to be an even number because we doubled the total number of primes. Like a more interesting example would be if we had like an odd number of primes to begin with. So let me just do an example like that. Likewise, let's see, like 45. What's 45? Isn't that like 3 squared times 5 or something? Yeah? Times 5 to the first. And 45 squared, whatever that is, 45 squared is equal to, what's it going to be equal to in terms of those primes? Yeah, 3 to the 4th times 5 squared. You see that there are 4 3s and 2 5s. 4 plus 3 is, or 4 plus 2 is 6, which is an even number, yeah? So I have an even number of each one of those, and I add together a bunch of even numbers, I end up with an even number, yeah? All right, so there are 6, right? 6, oops, I'm running out of room here at the bottom. 6. Oh man, come on now. Okay, so there are 6 primes here. Okay, 6 primes here. Okay, and let me just say that that's an even number of primes. An even number of primes. What is the conclusion here? If I square any number, its primes all get doubled. And therefore, like any number that is a perfect square has how many prime factors total? An even number, yeah? Any perfect square has an even number of primes total as factors, yes? So let me just go over to the next page, okay? So we see that any perfect square has an even number of primes in its factorization. Okay, of course, some of those primes are, repeated, but each actually, let me just say even more than that, actually, each distinct prime factor occurs an even number of times. That's what we actually saw, right? So for instance, the number of 2s was even, the number of 5s was even, the number of 3s was even, and therefore, when I added those together, I get an even number of prime factors. Each distinct prime factor occurs an even number of times. Okay, so what is that? How does that help us? Let me just kind of start to get the ball rolling. So since P times, what was it? P times B squared is equal to A squared. Help me out here. What is the problem with that equation? There's going to be an odd number of primes on the left and an even number of primes on the right of that equation. Yes? Okay. We would have an even number of primes on the right, but an odd, okay, because B squared itself has an even number of primes, yes? And if I just slap on one more prime, that's going to take it to how many primes? An odd number, yeah? But an odd number of primes on the left. But that is just garbage because this was supposed to be the same number. That's why we wrote equals, correct? Yeah? So that is impossible. Primes on the left, which is impossible. Okay? So what do we conclude? So what's the conclusion? All right, the problem was our starting point. We said that the square root of P was rational, yes? Okay? So the conclusion is that the square root of P is irrational. So that's cool, okay? Because, for example, the square root of 5 is irrational. Square root of 2 is irrational. The square root of, the square root of 41, that's prime, right? Yeah, square root of 41 is irrational, etc. That's interesting. Now, actually, here's what's even more interesting, y'all. The proof that we just gave doesn't just work for a single prime, but a product of, think about it for a second, but a product of how many primes? Really, the key wasn't just that there was one prime sitting here. The whole argument would work even if I just had an odd number of primes multiplied together. Does that make sense? So if I had 3 primes, like 2 times 3 times 5, that odd number plus an even number still would have been odd and would have messed everything up. Does that make sense? Okay. So actually, here's a little corollary for us. Corollary. If an integer n has an odd number of primes, then what's the conclusion? Square root of n is what? Is irrational. Irrational. Okay? And the proof is exactly, I mean, what you could say is, look, the argument is exactly the same. There wasn't anything special about there being 1 prime. That just bumped us from an even number to an odd number. Well, I could just have any odd number of primes, okay? So that's really cool, because now I can say things like, for example, the square root of 2 times 3 cubed times 5, right? Like, how many primes do I have sitting there? 1 plus 3 plus 1 is 5. Does that make sense? That has to be irrational, is irrational. Okay? The square root of 2 times 3 times 5 times 7 squared times 11 cubed. Okay, let's see. Whatever that number is. 3 plus 2 is 5. 6, 7, 8. That's not quite right. So, I mean, I could like bump maybe this power up here to like a 2 or something like that. And then I have a total of 9 primes here. Does that make sense? So I have no idea what number that is underneath that square root. It's fairly large, but that number is irrational. Okay? I don't know. I think that's pretty cool. Yeah? And that's all because we just thought about the number of prime factors that something has. Okay? Any questions on that? Please ask. Ask questions. That's interesting. Mm-hmm. No, not necessarily. No, well, actually, no, not necessarily. That will happen sometimes if I have an even power on each one of the factors, because then it will have a perfect square root. For instance, if it was like 2 to the 4th times 3 squared, if I take the square root, I could just half each one of those powers and I would end up with like a perfect integer, yeah? But I don't know that you can necessarily say that this, right? For instance, you know, is the square root of 2 times 3 squared times 5, is this thing rational? Right, because look, look at this. That has an even number of primes in it. Does that make sense? Well, I don't think so, because look, isn't this the same thing as, like, if I take the square root of each one of those things separately, isn't that the same thing as 3 times the square root of what? Square root of 2 times 5, okay? Now, the corollary that we have says that if you have the square root of an odd number of primes, you're guaranteed to be irrational, but the square root of 10 is also irrational, okay? 3 times the square root of 10 would also be irrational, but that would require a different proof. Does that make sense? We're just able to conclude right now that the square root of a product of any odd number of primes is irrational, but we don't necessarily know that just because you have the square root of an even number of primes. So square root of an odd number of primes implies irrational. Square root of an odd number of primes implies question mark, right? Okay, so we know that, you know, square root of an odd number of primes implies irrational, right? It implies that that thing is actually irrational. But we don't know what the square root of an even number of primes implies necessarily. In fact, there are examples of things that actually end up being irrational, even though it's an even number of primes. Okay? It's a good question. So this thing right here actually is irrational. Okay? Yeah.
But you can tell me if this is too off irrational numbers, the number of irrational numbers, like that infinite amount of irrational numbers, and bigger than like natural numbers. Like that infinity is bigger than the other, or like
Well,
all
okay.
real numbers.
So the number, okay, so like, yeah, that's right. And we'll talk about this more in depth later, but that's a good point. The number of irrational numbers, which is infinite, can be shown to be strictly larger than the number of rational numbers, even though that's infinite. So we'll talk about levels of infinity eventually. Yes, that's actually a true statement. Yeah. You feel like that's not possible?
I feel like I could write all the real numbers, like.
You feel like you could write down all the real numbers systematically? No, there's actually a proof that we'll go through. It's called Cantor's diagonalization argument. And actually, that's one of the last chapters in Journey Through Genius. And Cantor's diagonalization argument tries to do that, Monique, and he gets in trouble on purpose. So it's a contradiction proof, actually. Yeah, I'm sure the reason it doesn't work is because of some kind of diagonalization argument, like what Cantor did. But yeah, we'll talk about levels of infinity, and that there are indeed actually infinitely many levels of infinity. Okay, that things can just keep getting bigger and bigger and bigger in terms of the size of things that are in there. But it turns out that there are some tricky questions even in there that really delve into kind of philosophical issues. There's some weird stuff. I mean, Cantor himself, actually, who first started doing this, literally drove himself insane multiple times. What he was trying to do was he was actually trying to show, okay, so like you have the rational numbers, right? And then you have the real numbers, which he called the continuum, okay? Actually, the continuum was really like an interval of numbers, but it's the same size, okay? You had the continuum, and you had the rational numbers, basically, or even the integers, if you want to look at those. And what he was saying is, okay, I can show that the rational numbers are strictly smaller than the real numbers in terms of size. But is there anything in between those two? Like, is there a set that is like strictly bigger than the rational numbers, but strictly smaller than the real numbers? Does that make sense? Like, is there something between those two in terms of its size? Or does every set I have that contains the integers, is every set I have either just the same size as the integers or the size of the real numbers? Or is there something that falls between? And he drove himself literally insane multiple times trying to prove that it was either one way or the other, okay? At first, he thought he had proved that there's nothing in between. And then one of his friends said, oh, hey, that's not right. And he was like, oh, man. And then he ended up in the loony bin, okay? And then later on, he was like, no, I actually found something in between those two. And another one of his friends said, nope. It's the same size as one of those, or like, no, that doesn't work. And he was like, oh, and then he ended up in the loony bin again. The rational numbers and what? And the real numbers? Well, I mean, yeah, I mean, he's just trying to build something that has size strictly in between those two. Because, I mean, you can imagine just throwing in a few of the irrational numbers like square root of 2 and 5, and square root of 2, square root of 5, square root of 7, square root of 37, whatever you want, right? You could slap a few of those things in there systematically, and you would hope that you would kind of build up something that might be between the two. But what he found out was he couldn't prove it. And then someone came along in the early 20th century by the name of Kurt Gödel, O with an umlaut on top, right? A German dissident. He kind of came to the United States, and he actually proved something called the incompleteness theorem, which says that if you work in any mathematical system that has something as complicated as the integers in them, okay, which we do all the time, we're constantly working with integers, that you are bound to stumble upon mathematical statements that are undecidable. That is, statements that you can't prove or disprove, and you just have to accept them or reject them on blind faith. Now, mathematics had been totally thought to be resistant to any such thing. I mean, are you serious? I have to accept this really complicated statement on blind faith or reject it? And that's what the incompleteness theorem says, that you're bound to stumble upon undecidable statements. You just have to either say, okay, I believe it, or I reject it. And in like 1969, there's a logician by the name of Paul Hallmush, or actually Paul Cohen, who actually proved that Cantor's thing that he was trying to mess with, it's called the continuum hypothesis, is an undecidable statement. Which means that you either have to accept that statement on blind faith or reject it. So it's kind of a sad conclusion to the story, because was he ever going to prove it, Monique? Was he ever going to disprove it? He was just going to have to either accept it or reject it on blind faith. But it wasn't until after Cohen came along that that became apparent. Okay? So that's something that we will study later on, but that's a good question. It turns out that the irrational numbers far outnumber the rationals. So if I had a swimming pool, actually an infinite swimming pool, filled with marbles, an infinitude of marbles, and all the red marbles were rationals, red rational, right? And all the white marbles were irrationals. I could like dive into that pool and I could search for all eternity, and the chances of me finding a red marble anywhere is not good, okay? The irrational numbers so far outnumber the irrational numbers so far outnumber the rational numbers, which is sort of surprising, right? Because we have to work so hard to even find irrational numbers. I mean, for crying out loud, we just had to give a proof that the square root of 2 is irrational, yes? whereas rational numbers are trivial to come up with. We're just like, oh, 37 fifths. I mean, for crying out loud, that's obviously irrational, yeah? But the irrational numbers just blow the rationals out of the water, okay? That's a good little sidebar discussion for sure. But we'll talk about that more in depth later. The next section, after we get this proof stuff behind us, we'll talk about sets, okay? And set notation, and we'll talk about how sets work and how to count the number of things in a set. And that's what Cantor was obsessed with, okay? Other questions? Other questions? All right, well, here's what I want to do. We have a few more minutes. Yeah. Back to sharing this. Okay, we've already talked about this before, but to prove P if and only if Q, remember we have the biconditional that goes both ways. What we have to do is we have to do two proofs. Does that make sense? It's do P implies Q, and then the second half of the proof, you will do what? Q implies P. And that all comes down to the fact, that actually this thing is equivalent to P implies Q and Q implies P. That's literally what the if and only if means, okay? The biconditional. So a biconditional statement will have two sections to the proof. You know, working from P to Q, and then the second half working from Q to P, all right? Interesting. Okay, let's talk through this. Why is this proof wrong? This proof that 1 equals 2. And here I kind of tried to do it in like a 10th grade sort of statement reason format. Okay? A equals B is what I start with. Therefore, if I multiply both sides by A, I get A squared equals AB, right? Okay, what's next? Ooh, somebody is saying it divides by 0. Ooh, let's see if that's right, okay? So then what did I do in part 3? I just subtracted B squared from both sides, yeah? Step 4, I just factor both sides. On the right-hand side, I factored out B. On the left-hand side, I did a completion of the square factorization, a minus b times a plus, or actually not completion, like difference of square factorization. And this is the part where Connor just said, hey, please don't divide by 0. A minus b, I cancel from both sides. But I can't do that unless I know that thing is not 0. Does that make sense? I can't like cancel 0 from both sides. Yeah. So that's the step where it goes wrong. Then I get like a plus b is equal to b. If I replace a by b, I get 2b equals b, and I cancel b, which is apparently not 0, and I get 2 equals 1. So it's the cancellation of a minus b that's sort of the problem here. Does that make sense? You have to be kind of on high alert about those kinds of things. So that would be a fun thing to think through together. Okay? Let's see. There's other types of proofs. I told you there's like proof by cases. What is WLOG? What does that mean? Without loss of generality. There's existence proofs, proving that something exists. That's kind of, you know, that's exciting. And then disproving something by counterexample. Okay? So for instance, earlier we were wondering if the square root of an even number of primes is always rational. A disproof of that by counterexample would be to find a situation where the square root of an even number of primes is irrational. And I claimed that there is one, namely like the square root of 10. If you do square root of 2 times 5, that is irrational. Okay? Look, you would do cases. One way you could prove this statement, have you ever done like the minimum of 3 numbers? You know, you want to do the minimum of A, B, and C, and you kind of do that by first taking the minimum of B and C and then taking the minimum of A and that minimum. Does that make sense? And then that should, in theory, give you the minimum of all 3 things. Yeah? But then you might say, wait a second, does it depend on whether I look at the minimum of B and C first or the minimum of A and B first? You see what I'm saying? The answer is no. And one way that you could do this is by cases. You kind of organize A, B, and C and assume that like A is the smallest, and then maybe B is the smallest, and C is the smallest. And in each one of those cases, you would get a different result. I'm not going to go through this one in any kind of detail, but you could prove this by cases. Yeah, you could kind of say, well, what if A, B, and C are organized this way, or what if they're organized in this other way? Then your proof would proceed accordingly, okay, by those according to those cases. Without loss of generality proof, here's an example. So prove that 5x plus 5y is an odd integer when x and y are integers of opposite parity. What does that mean? Yeah, one is even, one odd. Now you might say to yourself, oh no, which one's even and which one's odd? Now, sort of a silly way to do it would be cases. You would say like, okay, x is even and y is odd. And then case 2 would be x is odd and y is even or something. But look at the symmetry here. Do you see that like it says 5x plus 5y, right? I mean, does it really matter which one is even and which one's odd? No, the proof will be exactly the same. So here you could actually do a without loss of generality proof by just saying, without loss of generality, x is even and y is odd. And then you would kind of proceed from there. Does that kind of make sense? A lot of times you will run into a situation that is so symmetrical that that it doesn't really matter which plays which role. And that's what this one is like. Okay. Any questions on that? I'm not going to go through that one in any detail either, but I just wanted to show you the sort of situation you might use without loss of generality. Okay. WLOG, what's funny is like every mathematician kind of knows what that means, right? Without loss of generality. Yeah, I know what that means. Kind of like QED, right? So prove that there exists, this is like an existence proof. Prove that there exists a positive integer that equals the sum of all the positive integers less than it. Can you guys just give me an example? So there exists a positive integer that equals the sum of all the positive integers less than it. This is an existence proof. What works? Well, sort of. One technically doesn't have anything. It doesn't have any positive integers less than it. 3. Okay, here's the proof. 3 equals 2 plus 1. QED. Okay? These are literally sometimes really easy. Showing that something exists really amounts to kind of building an example, just kind of thinking about it. Yeah? So that was a nice proof. Prove or disprove. Okay, this one's kind of tricky, and actually we'll come back on Wednesday and talk about this one before we move on to stuff about sets. Prove or disprove that if A and B are rational real numbers, then A to the B is rational. Okay, so A and B rational. Actually, you guys probably already know an example. So if A and B are rational, does it follow that A to the B is rational? If A and B are both rational, does it follow that A to the B is rational? Given what we just talked about, like not very long ago, like in this very class. Square root of 2? Irrational? And yet, that's like 2 to the 1/2. Yeah? So do we believe this or do we give a disproof? Yeah, here's a disproof. The disproof is by counterexample. So A equal to 2 and B equal to 1/2 are rational. But what? Yeah, which is the square root of 2 is irrational. 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 Exclamation point. Yeah? So there you go. There's a more interesting problem I thought I had in here that I wanted us to work on, but we'll revisit that on Wednesday. Okay, I just wanted to expose you to kind of the different sorts of proofs that one tends to do, right? Direct proofs, proof by contraposition, proof by contradiction, proof by cases without loss of generality proofs, existence proofs, proof by or disproof by counterexample like we just gave. These are the sorts of things that one tends to do. There is one type of proof I haven't talked about yet that someone said seems like something a lawyer came up with in one of your in one of your reflection papers, and that's an induction proof. Okay, but we'll talk about that a little bit later after we deal with some other things. Okay, all right. I'm going to stop there for now.